All right, welcome everybody to today's guest speaker talk. Today's speaker is Dr. Natalie Caciagli. She is the Senior Manager of Resource Geochemistry at Barrick Gold, where she works on a wide range of international projects in exploration, mine planning, resource estimation, geometallurgy, and production. She combines compositional data analysis and data science techniques, and she has applied artificial intelligence and machine learning tools to mining projects, integrating data in geochemistry, lithology, alteration mineralogy, and metallurgy. Natalie has a Master of Science in Geology from the University of California, Los Angeles, and PhD in Geology from the University of Toronto in Canada. She's an adjunct faculty member at Laurentian University and a member of the Canadian Securities Administrators Mining Technical Advisory and Monitoring Committee. Her experience in mining analytics spans North America, South America, and West Africa. So I would ask everybody to make sure that your microphones are muted. And if you have any questions, you can type them in the chat box. And at the end of the talk, I will open the floor. Either I read the questions or you can ask your questions by turning on your microphone. So Natalie, you can start your talk.
Thank you. Okay, so thank you for inviting me. I'm really happy to participate, especially in all of these weird times, as much as I can with the geoscience community. I know it's been a weird year. In my life, this year has actually, these last couple of months have actually been really, really busy, because with all of our exploration teams grounded in various parts of the world for various periods of time, there's a lot of focus on people reviewing their data. So this is actually, a really good time. We've spent so much time collecting data, and sometimes the pressures are on to keep those projects moving and the programs moving, but to be able to sit and actually immerse yourself in your data and explore it, and test and use it to test some hypotheses takes time, and so this is what I've been doing quite a lot of over the past couple of months. So I guess just an outline of the talk. First, I'll talk about data types and limitations of the data. I will focus on the workflows that I use most often, which is bringing the geochemistry and the geological data into what I call a geochem hyperspace, which is I build with principal component analysis. So I'll talk a little bit about how I build it. So what I want to query from that data. So what am I going to be focusing on, or what I want to be ignoring, and how I use it in a variety of workflows. So validating logging codes, filtering data, selecting features, and then I'll walk through 4 examples. The example 1 and 2 are specifically related to geochemical data. With example 3 and 4, it's supervised classification using a combination of geochemical data and also logging data. And example 4 is just logging data. Okay, let's move on. All right. So the first step that I usually ask is what is the purpose of the analysis, or what is the question that you're asking of your geochemical data set? What is the hypothesis that you want to test? And it's important to have that clear in your mind, because now you need to look at your data and assess whether you have the right data for that. So in terms of that, it's what lab methods were used to assay the data, how was that area sampled? So are we sampling on composites? Are we compositing our samples, and now are we asking to see marker beds or marker horizons in data that we've, samples that we've composited over 20 feet? Are there any biases in the data set? So have we only sampled the sort of footwall of our ore body, or have we looked at the, have we actually sampled everything? Are we only sending geochemical data that's above cutoff? Or are we, are we not sampling waste? So it's important to understand what's inside your data set. And that's really what I mean, with the, metadata. Look at your metadata, look at your metadata. Make sure you bring that metadata in with your geochem. So whether it be logging, whether it be sample intervals, whether it be alteration. So it's very important to understand what you're dealing with. And then the next thing is, if you're dealing with geochemical data, you need to consider that it is compositional data. So I'll touch on that a little bit more. So first step, data types. Lab methods and digest type. These are the the two that I have to deal with sort of most commonly when we collect data, geochemical data on samples around an ore body. There's typically two methods that are going to be used. Don't collect too much whole rock data. Usually it's either 4-acid digest data or aqua regia digest data. And it's really important to understand, particularly if you've been handed a table that mixes these two methods, it's really important to understand that these are fundamentally different. They digest the minerals differently, which means you're essentially producing a geochemical assay of different parts of the rock. So you can't always compare, mix 4-acid digest data and aqua regia data, because it's essentially like you've got two different samples. 4-acid digest will digest almost everything. It will leave minerals like zircon and monazite and rutile incompletely digested. They might be partially digested, but they will not be completely digested. Aqua regia will digest carbonates, sulfides, some oxides, some variable proportion of other silicates depending on acid strength and temperature and time and grain size and just morphology of those grains. Are they fractured? So it's a bit random when you look at some elements in an aqua regia digest. So, and it depends on your rock. So if you're looking at silicate or sedimentary rocks, I've got a really long list here of, what's going to be different in 4-acid versus aqua regia. It's maybe easier just to look at the list of what's not going to be that strongly affected, which are for gold deposits, your pathfinders generally. In carbonate rocks, you can add calcium, magnesium, manganese, and strontium to the list of elements that won't be that strongly affected. But by and large, you really need to be understanding of what's been sampled and how it's been sampled when you look at your geochem data set. The next thing, once you've kind of wrapped your head around how your data has been produced, it's to now look at what's missing from your data. Something is always missing. In data science, there are sort of 3 terms for classifying missing data, not always intuitively named. There's data that is missing completely at random, and this really talks about data that's missing where the reason for the missing data points is not related to any of the data. So in this case, an example what I sometimes have is where there's systematic gaps. So only maybe 1 in 4 holes were sent out for geochemical analysis, or maybe only every other interval was sent out for geochemical analysis. Sometimes this happens for cost saving measures. As long as it's been really systematic, when the data are missing completely at random, an analysis performed on this kind of data set will usually be unbiased. So, you know, that you don't have to worry too much. You probably have sampled a little bit of everything, even though you're just not sampling that densely. If the data, there's another type of data is data that is missing at random. This one is the one that's kind of counterintuitively named because the reason for the missing data points is related to the observed data. So it's really not random at all. Intervals have not been sampled because it was a certain lithology that was perhaps, you know, viewed to be not a favorable host lithology, or it's an alteration type that was viewed to be not important, or maybe it was waste, or maybe it was below cutoff. But when the data are missing in this way, you are dealing with a biased data set because you're not seeing everything. You're only seeing part of the picture. And the dangerous thing happens is when you don't really understand this and you proceed into an analysis and you start to make some conclusions. The last kind of data missing is data that is missing not at random. And this is when the reason for missing data points is related to the data. So basically it could be because it's below detection limit. So that data point is missing because of what that data point represents, below detection limit data. And we have different tools to deal with this. You can generally consider yourself maybe not really to be biased. If you have some of this data, you can fix that problem. So I'm going to just go back again because this is really key when data is missing at random to kind of understand how that can lead you down a bad path. A good example, I think famous example of this is during World War II, the RAF lost a lot of planes to German anti-aircraft fire, and they thought, well, we can probably support a little bit more armor. We can add some weight to these planes. So where should we put this? So they took a survey. So they built a data set and they looked at the planes that returned from missions, analyzed damage patterns, and then thought, maybe we should put the extra armor on the areas that attract most fire, right? So here's a little diagram that shows, you know, the tails, the wings. But now let's consider what's missing from our data set. The planes that didn't come back, the planes that were shot down and didn't actually come back is what's missing from the data set. So what you really want to do is armor up the areas that on average don't have any bullet holes in here, because, whoops, those are, oh no, now what have I done? Those are the planes that, didn't come back. And that's why we're not seeing them. So if we could armor up these, maybe we'd get more planes back. So that's what's missing. So that's the dangerous bias in your data set. So it's always important to consider your data set very carefully, which is where having that metadata is really important so that you understand what was sampled. The next kind of missing data, like I mentioned, it's the missing not at random. So this is really in most of the data sets that I deal with. It's below detection limit data, and there's lots of ways to deal with that. One common way is to simply replace any values below detection limit with half the detection limit or a third of the detection limit. The problem with this is that if you're dealing with quite a bit of data, so what I'm showing the column on the right here, is the percent missing data from a PXRF data set. So in PXRF, if you're not counting for long enough, you can actually just generate a lot of noise in a lot of elements and end up with up to 20, 70, 80% of your data below detection limit. So you don't want to, if I had to throw out every single sample that was incomplete, or element that was incomplete, I'd basically only be left with iron. There'd be very little that I could do with that kind of data set. But I can take a certain percentage and say, okay, well, I'm happy to impute those values. But if I just did a simple replacement, that's still 5% of my data or 17% of my data for one element that's going to have an identical value. And so that's going to skew the matrix, the correlation matrix or the covariance matrix. So it makes it difficult to work with. There is in R a routine, several routines actually. The one that I like to use is this expectation maximization. I use this routine to impute values below detection limit. And what it does is it basically fits that distribution, the expected distribution of that element with values that are in line with the detection limit, but maybe not all identical. And so, it is, someone asked about this before. You are making up data, but you're still bringing a number that is below detection limit. So it might just be, a couple it might just be a couple of decimal points, percentage points off of the detection limit. But when you're at the detection limit, it's important to understand what the data that's at the detection limit, your signal to noise ratio is so high, your variance could be 2 or 3 or 4 or 5 or 10 times that number. You really don't know when you're at the detection limit what that number really is. You just know that it's around the detection limit. It's not until you get to 10 times a reading that's 10 times of your detection limit that you actually start to have confidence in what that number has a real meaning. So I'm not too concerned about imputing values that are below detection limit as long as they stay around the detection limit. It means that I can keep those samples in my analysis, and I won't be biasing my data set by throwing out a large proportion of samples. Okay. The last thing to consider when you're dealing with a geochemical data set is that geochemical data is compositional. This means it's a closed data set. And when I say closed, it means that they must sum to a constant. So 100 if it's percent, ppm if it's parts per million, a billion if it's parts per billion. So this means that they are only carrying relative information. So in that sense, what we need to do, we need to understand that the sample space that these compositional vectors exist in, it's different from Euclidean space that we would build with unconstrained data. So compositional data, it has its own structure, and this structure is known as Atkinson geometry or simplical geometry. And because it exists in this Atkinson space, standard statistical methods are not applicable to compositional data in their raw form. And this is something that's been known for a very long time. Actually, it was Carl Pearson in 1897 that first pointed this out. He said that, if you deal with a correlation matrix with geochemical data set, you're going to run into spurious correlations. And back in the 1960s, Felix Chase, he took up the cause again and pointed out that, multivariate statistical analysis on compositional data is not helpful because of these negative correlations that arise because the data is all constrained to a constant sum. So if you change something, it all has to balance out. In the 1980s, John Atkinson developed a log ratio approach to deal with compositional data. So that's basically, building on the fact that compositional data provides relative and not absolute information, and that we can use ratios to get around this. And this is something that I think geochemists have known for a long time. We generally look at element ratios. In fact, even if you're looking at rare earth elements, they are a ratio, they're normalized to chondrite. So, so we've always known that ratios is the best way to look at your data. But if we want to use a multivariate statistical analysis, we need something a little bit more sophisticated. So an example of the spurious correlation is, this is taken from Atkinson's 2005 paper. So let's say you've got two scientists, you give them a split of a sediment sample, and the first scientist is going to record the proportions of the sand, silt, clay, and water of the sample. And the second scientist is going to dry the sample and then record the proportions of the sand, silt, and clay. So it's intuitive to us that it's the same sample, so the proportions of sand to silt to clay should be the same. But if you actually build this kind of correlation matrix and you build it for the 4-part composition, and then you build it for the 3-part composition, all of a sudden you're dealing with a spurious negative correlation. The proportion of sand and to silt shouldn't matter whether you're looking at water or not. And we kind of know this. We know that, as long as we all work in terms of ratios, we'll be subcompositionally coherent. That's what this is called. And so the log ratio technique helps us deal with this. The other reason that this is really important is because just as there are issues with this correlation and compositional coherence, it's the distance as a metric for similarity becomes challenging. A lot of the methods that I use, building dendrograms or hierarchical clustering or k-means clustering, uses a distance between points as a measure for similarity or dissimilarity. And if this Euclidean distance doesn't really represent what's happening with the samples because it's constrained to 0, it's going to make any kind of clustering or distance metric meaningless. And so it's really important to understand that if you want to use distance, a measure of distance as a metric for similarity or dissimilarity, you need to bring your geochemical data into log ratio space so that the distances have meaning. And so there are a bunch of compositional representations. The one that I spend the most time using is the center log ratio because it preserves distance. There are other log ratios that could be used. The isometric log ratio is a good one. Balances, which are essentially the same as an isometric log ratio, you're choosing. So in the centered log ratio, you're taking every element and you are dividing it by the geometric mean of the total of that sample. In the isometric log ratio, you're choosing you're choosing what you're going to ratio against, and the same as balances. Balances, you're planning them. There are lots of places where you can make this calculation. I use R. There are two, R is open source freeware. There are two libraries that have packages to transform your data this way. It's Compositions and Rob Compositions. There's also free software, CodaPack software, which will do this for you. Ooh, I'll move that. And then also IOGAS actually has brought in the center log ratio transformation. If you use IOGAS, you can go to the analysis tab and you can choose your, you'll choose your variables, and then you can run a centered log ratio. So it's picking up steam. It was first documented in 1986, but now you'll start to see more and more paper and more work talking about transforming data into real space. And partly, I think this has to do with the prevalence of people using cluster analysis or hierarchical clustering, where your measurements in Euclidean space have to be meaningful. So just to sort of finish up on the compositional data, just as there's problems between regarding between sample distances and between feature correlations, principal component analysis should not be applied directly to raw compositional data. So if you've transformed your data appropriately, the PCA will project the distances between the samples using that Atkinson distance, which will be subcompositionally coherent, and it will have meaning. So this is the environment that I use for unsupervised classification in my work. So I'll give you now a couple of examples. I'll walk through a couple of examples of that. But first of all, there's a couple of references. I can probably send this presentation. I guess it's being recorded, so you can go back and you can look up. These are some sort of important papers on how to apply these log ratio transformations to geochemical data. Okay, so PCA and geochemical hyperspace is what I kind of like to call it, is what I use to examine my geochem data and test hypotheses or answer questions. But first of all, the question would be, how are you going to build this geochem space? What are you going to specifically focus on, and what are you going to broadly ignore? So what I'm showing here is a variation matrix. So it's basically the covariance matrix of the additive log ratio transformed data. We're basically just taking the log of every element against every other element here, and then using that distance to build a dendrogram. And so here's like the full data set that I have for one of these projects. And you can see here all of the Pathfinder elements, all of the elements that are related to mineralization are clustering in one branch, and everything else that might be related to lithology and alteration are kind of sitting in this other branch here. So if I run a PCA on this, I will get almost 40% of the geochemical variability in my data set is going to be described by that one branch on that dendrogram and everything else. So this is an accurate representation of what that data set is. But if my purpose of doing this analysis is to look for marker beds or to validate lithology and not necessarily deal with the mineralization at that point, it would be better for me to examine the data set in the absence of these elements, because these elements are swamping out the variability that is seen everywhere else. So what I can do is take these columns out of my data set, rerun that center log ratio transformation, and then focus on broadly ignoring mineralization and focus on lithology. So now I've subset that data, rerun my center log ratio. Here's the dendrogram. I'm going to be not going to this meeting. Here's the dendrogram that arises. And so now you can see that there's a lot more spread in these in this data set, and I can start to subset this geochem space. So this is a plot of principal component 1 and principal component 2, and these are the vectors, so the elements that make up that. And so I can start to see, okay, this part of geochem space probably is coming from mafic derived sediments. Here I can see clays. Here I can see a signal from felsic derived elements. So if I brought my points into this space and they sat in this geochem space, I could probably start to get a sense from, you know, what the sediments were originated from. So this is what I mean, a better geochem space. So recognizing that geochemistry is a proxy for mineralogy, mineralization and alteration processes are going to produce distinct geochem characteristics. So if I want to visualize the variability of these processes, I can build myself a space from principal component analysis, and I can look at my data in that geochem space. So for validating logging codes, I would probably take out any samples that have any gold values above background. I would take out those elements associated with mineralization, and I would bring them into this principal component space. And so what I'm showing here is PC1 and PC2. All the points are colored by their lith codes. And this is kind of what you'd hope to see, is that everything that is one lithology is kind of clustered together in space. So you can see that, you know, this lithology is sitting in this space. This lithology is maybe a little bit more variable. It takes up more of this space, but generally this is your sort of first pass of looking at your logging with respect to geochem. So this is what you'd like to see. This is what you don't like to see. So this is where you would go back and say, okay, well, why am I seeing lithologies that are supposed to be the same sitting in very different places in geochem space? So what is this the correct geochem space to answer this question? Perhaps I'm looking at an oxide sulfide transmission. So yes, it makes sense that they would be logged the same, but geochemically they would be very different. So maybe I need to take out elements that would be strongly affected by that kind of transition. The other question to ask when I see something like this is, am I looking at all the same data? Are there lab method issues? Are there differences in digests or detection limits? Is that why I'm all of a sudden splitting my lithologies in geochem space? And also to sampling methods. Maybe not all of these are the same sample type. Maybe some of them are composites. And then of course, there's the, you know, are the logging codes adequate? Are they describing what we're seeing? Maybe we need to change how we use the codes to reflect what the mineralogy is and the geochemistry is telling us. So here's another example of validation of logging codes. So here's principal component 2 and principal component 3. So in this space, principal component 4 would be, or 1 would be coming out of the page. And here I've decided just to look at one style of alteration. And I'm looking at, so only illite smectite altered rocks, and I'm looking at the logged lithology. And so what I see here is that there's some inconsistencies, geochemical inconsistencies in the lith label. So samples that are logged as dacitic dome, and this porphyritic dacy andesite. So the crosses here, they're all kind of showing a lot of overlap in geochem space. So I would, think that perhaps these samples here are mislabeled. They need to be over here. There's maybe a couple more felsic or dacy andesites and dacitic domes that are overlapping. So I would say that maybe this is a problem of inconsistent lith labels. And if I'm going to do any kind of supervised classification with a neural network, using any other data, training a machine, this is going to cause this inconsistency in these lith labels are going to cause that AI algorithm to fail to predict these labels accurately, because we're telling it these two things are the same, but clearly geochemically they are not. Oh, what did I just do? Okay, let's try this again. All right, here's another example. In this case, I'm only looking at siliceous alteration, and you can see the dacitic dome plots in this space. There's this hydrothermal breccia, and it plots in the same space. So now the question is, maybe we're not looking at a different rock type. Maybe we're looking at a structure. So does this hydrothermal breccia need to have its own lith code? It should have a code. It's talking about something, but this maybe shouldn't be treated as a separate lithology. Maybe it should be treated as a structural zone. So these are ways to use the geochem space to validate logging codes and to generate questions or test hypotheses. So another example here. So this is an example of using unsupervised classification with geochemical data. So in this project, we had felsic to intermediate porphyry dikes, sills, and plugs, and they host the mineralization here at this project. It's a really structurally complex area. And so there's a bit of folding, a lot of faulting. And right now the intrusions are being classified, or were being classified, by phenocryst morphology. So basically the characteristics of the dikes. So they were logged as whether they were aphanitic, fine-grained, crystalline, whether the phenocrysts were crystalline laths or blocky laths. So you can imagine that over the course of a couple of seasons and with a bunch of different teams, this becomes a little bit subjective, exactly where you start to draw the line between a crystalline and a blocky phenocryst, or a crystalline lath and just a crystalline phenocryst. And so because not all of the dikes were mineralized, carried the same grade, it was really important to understand what was what, and also to be able to understand where the structures were. We really needed to see that sort of continuity of these intrusions, because that helped us see offsets on structures and whatnot. So I did an unsupervised classification. So I built my geochem hyperspace with principal component analysis of these elements. And the first pass was just to break out the lithologies based on geochem. So I wanted to reduce any misclassification of sediments or mafic intrusions. In some cases, the alteration has bleached out the mafic intrusions so much so that some of them would actually get logged as felsic. And so doing this first pass ensured that what I was putting into my bucket for analysis was going to be all geochemically similar. And for the most part, so this is the logging codes. These are the clusters that they fell into, and these were the logging codes. And you can see, for the most part, all of the all of the dikes fell into cluster 3. There were a couple of samples logged as Greywacke and a couple of samples logged as a mafic dike. But you know, going back and looking at those, they could have been misclassified. So now, without the other rock types and the other elements to swamp out the variability, I could now build a geochem space that would pick out the subtle variations in these. All of them are felsic dikes. And so building a geochem space with these elements, some of them are immobile trace elements and some of them are the major elements, but that allowed me to pull apart all of these clusters into, or all of these samples into 3 different groups for the most part. And when we went back and we pulled the core photos, or we pulled the core, we spent several weeks doing this. We could see that the geochem driven clusters did correlate to the phenocryst morphology, and that we actually only really had 3 geochemically distinct groups of felsic intrusions. We had this cluster 1, we had the cluster 2, we had the cluster 3. So the aphanitic and the blocky, and maybe this fine grained. And geochemically, those were the 3 phases that we could see in the geochem. And so that that helped consolidate the logging codes and improve the geological model, and help us understand both structures and the gold mineralization at this ore body. The next example that I have is around chemostratigraphy. So similar project, but this time looking at sediments. So here's a cross section from somewhere in the Carlin Trend. And in the Carlin Trend, we deal with a lot of mudstone, laminated limestone and mudstone. And it gets really hard to distinguish where you are when everything starts to look like this. I mean, you could obviously pick out the black mudstones, but this laminated limestone and mudstone of this mid-slope facies looks a lot like the laminated mudstone and limestone from the basal slope facies. The basal slope facies, though, is our preferred host lithology. So we'd like to be able to map this. And given all the structure and folding and faulting that we have here, it's a challenging environment to work in. And so we use chemostratigraphy a lot. So we basically build element ratios that will help us understand both the sort of detrital component, the biogenic component, and the authigenic component of those sediments. And we use these by basically plotting downhole element ratios. But in order to maybe make a more universal and faster classification, rather than having to go through and plot strip logs for every single hole, we tried to use geochem and unsupervised classification to help guide us. So building a PCA space from elements that I know would be responsive to those 3 different components. You could bring my samples into, here's principal component 2, principal component 1, and here you can see like the samples are pretty much clustering even without needing to use k-means. You can see that you've got a group here that seem to sit on the side of the principal component diagram, where the more micaceous, the elements that would make up more micaceous components of rocks would sit. And then you've got 2 groups of samples, 2 clusters here that correspond to maybe more reducing conditions. And so looking at core photos, plotting up strip logs, pulling core, we could see that this cluster here corresponds to more micaceous rocks, which is that sort of mid and upper slope facies. And then we've got our basal slope facies. This is our host lithology. This is the one that we want to be able to more robustly identify sits in this space. And then here we've got distal slope facies. So these samples were actually all sitting on the footwall of the major fault. And so clustering in this space and clustering these rocks lets us more take away some of the subjectivity of even people making calls on squiggly lines down down strip logs. We can see that where we look at all of the elements in multivariate analysis, we can now create a cluster that grabs the basal slope facies and the mid slope facies here. And here's an example. The clusters are back flagged onto this drill string here, and we had one of our best geologists go back, pull this hole, and relog it. And so there's his shape based on the relogging. And the geochem clusters reflect this very well. So this is a good, robust, standard way to classify these rocks. All right, next example. This will be an example of using geochemical unsupervised classification and supervised classification. So this is a PXRF data set. And, first of all, looking at all of the metadata, making sure that I'm comparing all the same samples and that the analyses are all robust and good. And then dealing with the below detection limit data. So I prepped this data set by removing some samples, removing some holes, and then just basically focusing on data that I felt that I could impute and still have a reasonable reasonable data set to show some kind of geochemical variability. So the geochem space here was built from those 4 elements. I'm showing, actually there's more, I think there's 6 or 7. This is principal component 2 and principal component 1. And so here's one of these cases where k-means clustering is useful. It's not like the sediment plot where things spread out naturally and neatly. In this case, the k-means clustering was actually quite helpful. And here it all looks like it's all very symmetrical. The k-means likes to try to make the different clusters the same size. It doesn't always, but it has a tendency to do that. So it's really important to validate your clusters. So in this case, I came up with 5 clusters. Putting them back into the geology model, so back flagging the drill holes, the drill hole strings with the clusters, we could see that 2 of the clusters sat within this grade shell here. And so we could interpret them as alteration, so clusters that were related to alteration. 2 of the other clusters sat outside this grade shell. And so we interpreted them to be the host lithology. And there was some variability within them, but the purpose of this analysis was really to understand alteration related to gold mineralization. So we didn't focus too much on these other 2 clusters. The reason this was important is because we didn't really understand the alteration domains, so we couldn't come up with very robust gold estimation domains. And when that happens, it means that your gold estimation domains are just based on they're just numerical, and they're based on statistics and not necessarily in a geological context. And this is a really good example in this shot here. So the grade shell, as you can see, crosses over this boundary of this shear zone. We knew that this shear zone was a hard boundary, so it shouldn't be. We could make it a hard boundary with the resource model, but it still means that we don't really understand where our gold is and why it's there. So we wanted a geological context. So bringing the geochem in, we had now these geochemical domains that that looked like they were mapping out the alteration related to mineralization. So the problem there is I have geochemistry on this PXRF analysis on a lot of holes, but not all of the holes. As you can see from the beginning, I had to even throw out some holes just because they were diamond drill holes or they had pre-collared. So I didn't have the sample support that the resource model needed. But we were really encouraged by what we saw. So we built we combined the two clusters and we built a domain where we had enough drill hole density to build a shape, and we could see that it was grabbing this 3 gram per ton grade shell, and perhaps in a better way because it wasn't crossing over the shear zone. So where I brought the supervised classification in is I looked at what data did we have on every single hole. Well, we had logged mineralogy on every single hole, presence or absence of 2 alteration minerals. We also had pyrite and pyrrhotite on ordinal classification, so ranked from 1 to 4. And we had mag-sus data. So I built a data set from all this data that we had, and I used a random forest algorithm to predict these geochem clusters. And by predicting the geochem clusters with this information, we could then look at the information that was most prevalent. So the features that were most important to those different cluster predictions, and we could see that looking sort of in hindsight, our alteration was related to a demagnetized zone, which we could get from our magnetic susceptibility data. We could see geochemical increases, but also interestingly, from looking at the statistics in the mineralogy data, we could see that it was an increase in biotite and biotite carbonate alteration intensity and quartz carbonate veining, as well as pyrrhotite mineralization that was related to our gold event. And this now provides a geological context for these gold estimation domains. So that would be, combining your unsupervised and supervised classification to increase your ore body knowledge. And the last example that I have is actually very similar to that. In this case, we wanted to similarly use a predictive algorithm for feature selection. So basically find the pattern from the logging data that tends to be associated with the structures that carry gold mineralization. And so we sort of found a bucket. So if we were dealing with mineralization, it was greater than half a ppm. If it was unmineralized, we said it would had less than half a ppm. So we segmented the data this way, and we looked at it by different lith types. And we wanted to see what were the variables that were most useful in discriminating these two classes. So what did the machine learning supervised classification need to use to correctly predict whether a sample was going to fall in one of these two bins? So we didn't really want to use this to predict where these features were. There's too much noise in these predictive variables, but we did want to see which ones would float to the top if we forced the algorithm to use them to predict. So what we had was, once again, presence or absence of minerals, the type of mineral, so whether it was disseminated or in a vein, structures, and then also ordinal ranking of pyrite, arsenopyrite, and stibnite. Oh, keep pressing the wrong button. There we go. So that's kind of what the data looked like. We had 114 possible combinations. We had disseminated sulfides, veins, totally mineralized, so I guess massive, and then 33 possible types of structures had been logged in the database. So this is where the machine algorithm becomes useful, because this is a lot of data to sift through to identify a pattern. And we actually had a much better classification of rate than I thought possible. We got to sort of 80% true positive over false positive rate on our predictors, and not surprisingly, it was gold mineralization was related to arsenopyrite and pyrite, which we understood, but what we wanted to do is pick out which structures were important. And we could see that this V3 and V2 actually ranked pretty high. And so that basically are veins that contain greater than 30% quartz, and also veins that contain stibnite or realgar. And so these things were sort of given back to the team at site. And earlier this year, they cut some trenches, and they realized that now that they had kind of gotten their eye in with the help of the AI, they were able to predictively log where these structural mineralized structures would be, and map them in the field. So just in summary, we've got what I hope you could take away from this is that your geochemical data is compositional data. It's closed, so you have to deal with it in a special way. You have to apply compositionally correct transformations, especially if you want to bring your data into any kind of algorithm where you're going to use space, Euclidean distance, as a metric for similarity. So this is important when doing principal component analyses or k-means clustering. I didn't talk on this, but there's a really good paper by Juan Carlos Ordóñez that looks at supervised classification, such as random forest or boosted forests, which are not sensitive to this data transformation. It's obviously, if you're not using distance as a metric for similarity or dissimilarity, you probably don't have to worry about the constant sum constraint. But if you're going to do any k-means clustering or t-SNE clustering or hierarchical clustering, you need to deal with your compositional data. So that's what I've got.
Perfect. Thanks a lot, Natalie. That was very interesting and very informative talk. So the floor is open for any questions. Anybody has questions, you can type in your question in the chat box, or you can turn on your microphone, because you'll be the first, and then you can ask your question.
I have one, Natalie.
Yeah, go ahead, Rebecca.
So at the beginning of your presentation, you were showing clustering both with random forest and principal component analysis. Do you often do them both at the same time and then draw conclusions from that? Or do you find that one or the other would be sufficient?
It depends on the question, depends on the data set that's given, and it depends on the data in the data set. So I think I always try both, and then just see which one is giving me the more geologically coherent answer, I guess.
Do you find that in those results, do you get some vastly different conclusions from one or the other, or do they generally agree for you?
They generally agree. If you're dealing with compositional data and you've dealt with it correctly, it's pretty robust. And so you should be getting the same answer in different ways.
Awesome, thanks.
Right. Any other questions?
It's lunchtime. It's always hard at lunchtime.
Hungry, I guess. Anyway, that's very good. I think we're just right at 12:30. So thanks a lot, Natalie. That was very good talk, in fact. So we recorded this. We hopefully post it online soon, and anybody has any, you can go back to the references and everything, and you can. That was very tutorial, nice talk. And thanks a lot, everybody.
Oh, thank you. Thanks for inviting me, and yeah, have a good rest of the academic year.
Yeah. Thank
Thanks.
you.
Bye.
Everybody, bye.